Welcome back. So, two of the hypotheses that we explored had to do with either the transport of material across the cell membrane, or alternatively with the production of ATP by ATP synthase. But the thing I want to remind you about that one was that ATP synthase lives in the membrane. So in both of those cases, we found ourselves asking the question: is there enough room in the membrane to accommodate the requirements either of sugar transport or of ATP synthesis? And I want to try to tackle that a little bit more formally here. This is brief; it'll probably take 5, 10 minutes, but I just want to kind of give you a sense of how we can think about something which is known as the surface to volume ratio. So let's start with the case of a sphere, and I'm probably not going to go farther than that, but you could do it for a spherocylinder, which is more like the shape of a bacterium, and that's actually very amusing. So the thing I want to note is that the volume is given by 4/3 pi r cubed, clearly, and the surface area is given by 4 pi r squared, and this implies that S over V is equal to 4 pi r squared over 4/3 pi r cubed, which is equal to 3 over r. So what's hiding behind that result that's very interesting is that if we have a surface feeding a volume, this is going to come up also when we do compartmentalization in enzymes. If we have a surface that feeds a volume, as the volume gets larger and larger and larger, thinking about the case of the sphere, we'll reach a point at which the surface is unable to accommodate the bulk demands. And that's what we want to work out here. So what I want to think about is if I have some membrane protein and the demands of the cell, so the bulk, maybe I should call it the bulk demand of the cell, is something like R bulk, which is equal to, just for example, number of ATPs per micron cubed per second. And I've told you that this is something like 10 to the sixth ATP per micron cubed per second. That's kind of a typical number to maintain cytoplasm. So the thing I know is that, and similarly, if I have R synthase is the number of ATPs per synthase per second, then that I can compute the total amount of total production of ATP, and that's going to be equal to sigma times R synthase times 4 pi r squared, where this is the areal density of proteins. Areal density of ATP synthase, for example. But this is a more general point. And so now, balance. We're going to use balance laws over and over and over again. So in this case, balance consumption and production. And so what that tells me is that R bulk times V is equal to sigma R synthase times S, where S is the area. So this gives me R bulk times 4/3 pi r cubed is equal to R synthase sigma 4 pi r squared, or that sigma is going to be equal to, this is a really nice clean result, R bulk over R synthase times R over 3. So what is that telling us? So this is telling us that as the area of the membrane, or as the radius gets larger and larger, the amount of the membrane, sigma, the number of proteins per unit area, has to go up. It goes up linearly with the scale of the cell. And the reason is that more and more of the surface needs to be decorated with these transporters or with ATP synthases in order to provide for the ever-growing volume which is consuming the ATP or the sugars or whatever. So we have this nice simple result, and I guess I just wanted to show you where this leads, and I'll probably give this as a homework problem. So what I'm saying is that, when I have a small cell, I can meet this demand of 10 to the 6th ATPs per micron cube per second by putting a relatively modest number of ATP synthases in the membrane. But as the cell gets larger and larger and larger, I reach some point at which I have to put so many ATP synthases into the cell membrane, there's no room for anything else. And what we'll find is that that scale is of order 10 microns or something. And so, I don't have I'm not going to show you the figure right now, but this is at least a plausibility argument as to why one needs mitochondria. Mitochondria take the burden off of the surface of the cell and now put it onto the very, very sort of variegated, invaginated membranes of the mitochondria, which are chock full of these ATP synthases. I just had a few more remarks to make here. So one of them is this, the lower left, which I find quite interesting. So this is from the proteomics, exactly the data we've been using all along. This is the intermembrane protein density in femtograms per micron squared. And the key thing that I want you to take away from this is that effectively the density of membrane proteins is roughly constant as a function of the cell size. So anyway, this was all by way of introduction to a theme which we're going to come back to again and again, which is the theme of balancing surface and volume considerations. Like I said, we'll have a very interesting time talking about this in the context of compartmentalized interaction.